Good evening, friends. Hello.
Good evening, sir.
I hope you can see what is there on the board here, right? So here you see there are three configurations that are possible: common base, common emitter, common collector. I think the schematic that I have given on the screen is quite clear. Okay. Hello.
Yes, sir.
Now, you have any questions here? Quickly ask. Okay, fine.
Working of all the three same, sir.
No, it will not be same. It will be different. It will be different. Different means now you see, you can see the block diagrams there. So these are called as block diagrams. Block diagrams means what is there inside this well, that will not be discussed. But you see the terminal conditions. So this is the input, right? And this becomes the output. Okay. Now there are three configurations. So here, as you can see, so you are feeding something at the input, then you are expecting something to come at the output. Okay, you are feeding something at the input, you are getting something at the output. Okay. Now, what are the important parameters you should consider, especially when you are dealing with these types of configurations? Okay. So here you see, we are looking at these three things. Can you see here? So the most important parameters will be input resistance, output resistance, current gain, voltage gain, power gain. Okay, these are the important parameters because we are going to use the transistor to get something, to get something here. Something here means, now you see, you will learn this in engineering. Now I want to have so and so voltage gain, I want to have so and so power gain, or I want to have so and so current gain. See, these are all the design specifications. That means now, you say, look, I want an amplifier to perform this task. I want the amplifier to perform this task. Okay. So then the task of the engineer will be to choose which configuration will suit so that the required output he gets. Okay, and therefore he has a choice. He has a choice of these three configurations. He accordingly chooses. Okay. Now, for example, so you see. So therefore now, when you use these configurations, they come with certain certain specifications. For example, now you see there is something called as input resistance. Input resistance. What do you mean by input resistance? See, now here to this input. Here to this input, supposing I give a voltage E. Okay, now all of you listen very carefully, right? All of you listen very carefully. Okay, now remember, in all these three configurations, we are going to use the transistor configuration as an amplifier. What did I say?
As an amplifier.
Then as an amplifier means, quickly your mind should work. What is that? The emitter base section. Emitter base section is forward biased and the collector base section is reverse biased. Keep this in mind. Okay, hello? Keep this in mind. Keep this in mind. Keep this in mind and think about it. Okay, so here I am measuring the current, that is entering. Okay, now what do I do here? I will change the input by delta Vin. So if I change the input by delta Vin, what happens? This current will also change by delta I, correct? Now the input impedance, I will denote it by R. Input impedance is delta Vin upon delta I. So for this change, corresponding change, you will measure this quantity. That is, you change the input by delta Vin and you observe the change in the current. You divide this by this. You get a quantity. That quantity we interpret it as input resistance. Correct? Hello? Now what you have to be careful is, now I am showing this as an open circuit. I am showing this as an open circuit. It is not the thing. Okay, there are certain specific like input resistance when the output is open, input resistance when the output is short circuited. Things like that will be there. Now, nonetheless, here you should know that the configuration is such that that these things are followed. These things are followed. For example, now if I take the CB configuration, then you see this and this will be common. So this will be the base. This is common base. This will be the base. Okay. Then obviously this has to be the collector and this has to be the emitter. Clear? Hello?
Yes, sir.
So then you also know that with respect to base, emitter is positive, that is it is at a higher potential, and with respect to base this is at a lower potential. Correct? And base is supposed to be the reference point. I hope I made all the signs very clear to all of you. Hello?
Okay.
So therefore, what you expect is the current will go out here, the collector current, corresponding collector current will go output here. See here, delta IN here means what? Delta IN here means what? Delta IE. Clear? Delta IN means delta IE. Delta for delta IN, the corresponding change in the collector current will be delta IC. Correct? Hello?
Yes, sir.
Now here I'm just giving you a model. So when I say input impedance, so here what is happening here is, of course you will have a battery here. You will have a battery here to reverse bias, resistance. All those things will come into picture. But that's not important for us. What is important for us is delta IC. And here you presume that there is a resistance here, which I will call it as Ri. Now that means I am not putting any Ri there. Now I am modeling. See, there is resistance between emitter and base. There is resistance between collector and base. There is resistance between emitter and collector. See, hello. See, you must. Oh, I am not having you in my presence. So I am finding it. So you see here, there is some current flowing from here to here, and there is some opposition here. So you will find a resistance here. Now there is some current flowing from here to here or here to here. You will find some resistance here. And there is also current flowing from here to here, down here, so you will find some resistance here. There is also some current flowing here also there is some resistance. Got it? So it's a complex thing. And these resistors are not lumped elements. These resistances are like forward resistance, reverse resistance, etc. So I am just taking the aggregate of all. The aggregate means it's not average or something. I am taking all these resistors into account and writing one simple resistance called as R. Is it clear?
Okay, sir.
Now look at this. So supposing this was open circuited, then the input resistance would have been simply V in upon I. But since the current is going like this, so what happens to this voltage? This voltage, see, now please understand this very carefully. Okay, I have a resistor here. Okay, and I have a resistor here, and supposing I have a voltage source. So what is this current? So this point I will call it as A, this point as B, and this point as C. I will call it as C. Okay. Now, so if I want to know what is this current will be what? VA minus VB divided by whatever is this resistance. Say RAB.
Yes.
Correct? That will be this current. This current will be VA minus VB divided by RAB. That will be this current. Correct? Hello?
Yes, correct.
Now assume that I am going to have a current source here. I am going to have a current source because you see what goes in the collector is a current source. Got it? Hello?
Yes,
Now you see this current, whatever is the current, that current will flow like this, or some part of the current can also flow like this. Got it? So therefore, this voltage VB, the moment this current source is connected, this voltage VB will come down. See, if the current was flowing like this, then this voltage would have increased. If the current is flowing out, this voltage will decrease. Got it?
Yes.
Hello, got it?
Yes, yes.
So therefore, if this voltage reduces, you can see here, this voltage reduces, then this current will increase. This current will increase, that is, this current will increase. So therefore, now for the same reason, this current increases means Ri will be small. Okay, that is why in this configuration you will have input resistance low. Did you understand?
Yes, sir.
Now look at this configuration. Look at this configuration, emitter-emitter configuration. So in this case, you can see that the base current is entering. Okay, if I draw Ri here, and the collector current is also flowing. So therefore, this voltage will increase. Therefore, this current will decrease. So therefore, now if you see from here, the input resistance will increase. That is why you say the input resistance is high. So it is low here, it is higher. I am giving you some idea about it, not in detail. You will learn all those things in detail in the higher classes. Right now, just for you to understand with whatever knowledge you have, I am just giving you some way of appreciating and understanding. Because in the examinations, they might probe a question, and if you go to the examination all by hearting things, then you will be in for a toss, right? It should not happen. You should know some way by which you should be able to get hold of which are low, high, etc. All those things. I hope I have convinced you.
Yes, yes.
Right. Thank you. Now here also you see. What is happening here. Now there is collector current. There is collector here. That means the collector current, the thing here, it means now as far as the current in the collector is concerned, there has to be current source connected. So therefore, this will see a current source in series. Now try to understand this very carefully. So you have this and you have a current source. Hello, are you with me? Right? You have a current source. Right? You have a current source. So here, see, here if you change the voltage V in, this current will not change. Whatever it is, only this current can change. Understand? So therefore, when you see from here, that means if this is open circuited, what is the impedance that you see from here? It will be infinity. Because whatever voltage you change, the current will not change. Supposing I keep this open circuit. Understand? So if there is a current source in series, then things you will start seeing very high impedance, and that is precisely what you get. That is why input impedance is very high. Did you understand? Hello, everybody there? Only Adil is telling yes, others are not telling. God save you. Now coming to output impedance. Okay. Now what is this output impedance? Okay. That is, you see, that is now in the same configuration. Now what do I do here? Assume, supposing, see here what do I do? Assume, I'm telling you to just assume. You are not supposed to connect any voltage source at the output. Output means you are going to abstract. But just to get an idea of what is output resistance, if at all, if you connect a source here, if at all you connect a source here, say V source, and if this changes by delta V, what is the amount of current that it changes? So a measure of this delta V, okay, I call it as VO, delta VO by delta I changes. Okay, that is what you call it. So here, if you look at it, the output resistance, so it will exactly be the ulta of this. So this is low, this will be very high. This is very high, this will be very low. And this is high, this will also be high. So whatever analysis I have told, you have to just do the same thing. Okay? The current source in between, etc. You will get those values. Good, Adil. Good. You are responding well, and I can feel from your response that you are really understanding and enjoying this. Anyways, others also should follow it, but I don't know for whatever reason you are not doing it. Done. Now current gain. Current gain is what? In this configuration. That means whatever current you send here and what current you get here. This current divided by this current. This current divided by this current. So you see, IC by IE is nothing but alpha. Okay, and that is AI. AI is current. So here, collector current divided by base current is nothing but beta. right? So AI for this configuration is beta. And here I am introducing one more term called gamma. Gamma is what? Emitter current by base current. Emitter current by base current. Okay? So emitter current by base current is gamma. Okay? So therefore AI is gamma, AI is beta, AI is alpha. Alpha is IC by IE, beta is IC by IB, alpha is IC by IE, beta is IC by IB, gamma is IB by IB. Okay? And this is less than 1, this is greater than 1, this is greater than, obviously. Right? Then voltage gain I have already explained to you. VO by V. Actually it is not VO by V. See, all these are delta VO by delta V. That's how you have to measure. You should not measure in absolute quantities. Even this. Delta IC by delta I. Like that you should measure. Okay, so you get here AV is equal to V naught by Vn. IC RL divided IE RL. Okay. And here you see IC by IE, you can write it as alpha, beta, gamma. So this is very simple. AV is equal to alpha into RL by RL. AV for CE will be beta into RL by RL. AV will be gamma by RL by RL. So suppose you understood this. I have done this derivation in my class. Please.
So that IB equal to beta times IC, sir. That will not hold when it is like constant.
No. Which one are you telling? Please repeat.
IC equal to delta beta times delta I.
IC is equal to
beta times I.
Beta times IB. Yes. What is the problem?
It will not hold like this.
It will not hold what?
We have constant current, sir. Will it hold that?
Oh, see. Everything that I have taught, you recollect. You please recollect. How was the diagram that was drawn? How was the diagram that was drawn? Listen. So here you were sending IE. Hello. This is emitter. This is base. So here there is a current that is flowing here. There is a current that is flowing here. What is this? This is beta times IB. This is the current source, but this current source depends upon IB.
Yes. But will that equation hold, or will delta is equal to beta times delta is hold?
No, once again tell which equation? Delta
is equal to beta times delta IB.
Is equal to beta times delta IB. You are telling this, no?
This one is correct, sir.
Very good. This is a wonderful question. Okay, wonderful question. Good. I'll explain. So now you have got beta. I am just writing beta here. This is an advanced question that you are asking, but I am delighted. I will definitely explain. This beta has got two values. One is beta DC and one is beta AC. Beta DC is IC by IB. Beta AC is delta IC by delta IB. Got it?
Okay.
So therefore, when the signal is varying, the input signal is varying, then you want to know what is the gain, you will go for this. But when you are doing the biasing, etc., you will go for this. And there is a small difference between these two values. This is small difference. Very good. See, this question shows that that you are understanding this, and it is so simple. It is so simple. If you attempt, everybody, that's what is science. Knowledge begets knowledge. You earn this knowledge properly, then the next set of knowledge, is in your mutti. 90% of the next set of knowledge, you will understand by yourself. If you have understood this, it's only the 10%, where you need help of the teacher. That's how, the learning continues. Okay, in good colleges, higher education, this is precisely what happens. The professor will tell you, I'm going to teach you this. You please come prepared. The student goes through all the literature. He would have understood 90% of it. So in the class, the teacher will briefly touch upon the points, and whichever point the student has not understood or confused, he will raise a question. The teacher will clarify, and that's it. The knowledge is complete. So in good colleges and higher colleges, the teacher will not teach us step by step or every topic there. He will just announce the topic, you have to come prepared, and that's it. So just get trained that way at this level, okay? You will enjoy the next level of education. Now, so you must have an andaz that the voltage gain in common base will be approximately 150, in common emitter it is 500, and in common collector the voltage gain is less than 1. Obviously. Clear? Because gamma is greater than 1, and here you see gamma RL by RL. IE by IG is very, very small. Okay, and therefore we will get it less than 1. Right? Power gain. What is power gain? What is power gain? Anyway? Anyone here? What is power gain? Power gain. So power gain is delta VO into delta IO divided by delta Vin into delta IO. This is the input power, this is the output power. Right? So this will be nothing but AV into AI. Clear? That's it. Very simple. Okay? That is power gain. So this becomes, okay, PO. So frankly speaking, it should be delta PO upon delta P. This is the power gain. So you see, you can enhance the power. See, in a transformer, even though there is step up voltage, you are not enhancing the power. The input power is equal to output power provided there are no transformer losses. But in the case of amplifier, the output power will be more than input power. Right? Why? Because the amplifier will abstract the energy from the DC sources. You are giving biasing sources now. From that it will take the energy and it will mix that energy with the input energy and throw it at the output. That's why your energy at the output will be enhanced. Did you capture what I said? So here you see AV. So if you go for this configuration CV, if you go for this configuration CV, okay, so what will be AV? AV will be alpha into RL divided by RL. Okay, and what is AI? AI is nothing but alpha. So you get here alpha square RL by RL. Okay, anyways, that is written here, you will get it. And AP here will be beta square RL by RL, AP will be gamma square RL by RL. Clear?
Yes, sir.
And the input signal. See, the input signal means supposing you are feeding the signal here like this. So in the case of common base, the output will also be in phase. But in this case, if the input is like this, the output is going to be like this. It will be out of this. And here also it will be same phase. And the application here is for very high frequency, for audible frequency, for impedance matching. Okay, so this is the important thing. Anyways, you have an idea. I have explained, how these things have come. I have not just given you statistics like this is low, high or something. I made you to feel and understand how this low, high, low, etc. will come and how these formulas are also evolved. I explained all these things in detail. So therefore, you don't have to buy it. You have to have, if you have enjoyed this chapter, and definitely you would have learned, and be confident, go to the examination, you will be able to enjoy answering questions in the examination. Okay, shall I move on, students? Now relation between alpha beta. Okay, well, basic equation divided by IC, you get IE by IC, maybe this one is 1 by alpha is equal to 1 by beta plus 1, or beta is equal to alpha divided by 1 minus alpha. Simple. So the basic equation remains same. So here IE by IB, right? You get gamma is equal to 1 plus beta, right? And here also the same equation possible. Do it, you get gamma is equal to 1 upon 1 minus alpha. Okay, you should be able to derive this. You can't by heart this, you can't by heart this, you can't by heart this. But with this basic equation, you do the appropriate division, then you will get the answers. Okay?
Yes, sir.
I hope all of you can read it. It is legible. Hello? Please read. Oh, Mr. Murthy, don't make it so big. Aram se read. If you don't understand something, you ask. If you say you have understood, I will move on. If you have any questions, I will answer. Shall I move on? Ominous silence. I am asking you, shall I move on, or you want any 2-3 more classes? You understood all these points?
Yeah, that transistor reverse bias is high.
You ask specifically. I will explain. All this I have written in Sankshipta. You have got many questions to be answered on these points. You understood the first point. I think I have explained this first point very clearly. You have understood. In transistor high compared to forward bias, remove from extra large extra first. This point also I think you have understood.
Sir, very high means what is high?
What is high? Where in a transistor reverse bias, as the transistor reverse bias is high as compared to forward bias. So the large carriers, the transistor reverse bias is high as compared to. VCC is higher than VBB, no?
Oh, okay, that's not high.
Right. That is potential Correct. Your question is right. CE configuration is widely used because it has large voltage gain and power gain as compared to other amplifiers. Okay, that is just a figure that they have written, but actually that is not necessary to put it like this. See, it depends upon the situation. Understand? It depends upon the situation. Because you see, now a particular design requires the CB configuration, you go for CB configuration. A particular configuration needs CE, you go for CE. That's it. There is no sanctum that you should do, but for academic point of view, they will say, okay, I mean at PU level, if they ask you why CE configuration is widely used, well, it has got large power gain. This you can write the answer. But frankly speaking, if the necessity is something, you can use other configurations. Okay. Now, in amplifier, negative feedback is used to stabilize the gain. Okay. Now, this aspect, did you grasp it? Understand this? Hello.
What do you mean by stabilize?
Stabilize. Okay. Now, aram se now understand this, because this particular thing is there for your syllabus in detail. Okay. So now here, it can be like this. Okay. So this is the input and this is the output. Okay. Now you see, I think all of you have driven at least a scooter. Everyone, if not a car. Hello.
Yes.
Everybody. Hello. Is there anyone who has not driven a automobile? Some scooter you would have definitely driven. Everybody.
Yes, sir.
Yes. Everybody in the class.
No,
Namans.
sir.
Noah. Somebody said no.
Sir.
No means what?
I not driven, sir.
Even a car, a scooter also you are not driven. Okay. Bicycle?
No, sir.
Bicycle? Bicycle at least. Abhinav?
Yes, bicycle.
Bicycle everybody have driven. Right.
Sir. Yes, sir.
Okay, done. Now, you see, say even a bicycle, if you say, you want to increase the speed. You want to increase the speed. So what do? You put pressure on the pedal. You put pressure on the pedal. So you put pressure on the pedal, the speed will increase. Okay? But now you are controlling the speed, you are controlling your cycle. Okay? That is, now imagine, you close your eyes and try to ride a bicycle. You close your eyes and try to ride a bicycle. So what happens? So you will just increase the speed. But whether the speed has increased to the required quantity or no, you will not get to know if you have closed your eyes. Got it?
Yes.
Right? So here you see in any system, if you see yourself, you have got eyes, and well, you have given input to a system. You are giving the input to the system, and there is some output. So you are giving input, and there is some output. Now, what your eyes will do? It will observe this output. It will see what is the output, and accordingly you will adjust the input. Correct?
Actually.
Okay. Now imagine. I will ask you to I think somebody is joining here. Now I want to touch this board. Exactly, I want to touch this board. So now you observe. This is my hand, right? So my brain is giving command to my hand to move, to touch the board. Correct? So my hand is moving. So I hope you are following what I am telling. So my brain is going to tell my hand to exactly touch the board. And you should touch the board such that it will not make a noise. Got it? You should touch the board, but it will not make the noise. Okay? For example, say I have made a point here. So now with this tip, I should touch the point. Okay? So now I should not make any noise. I should go and touch that point. So what will I do? See, my hand will start moving. So initially my hand will move. But now you see, initially my hand will move fast. But as I come closer, my hand will move slow. And then, I will slowly come and adjust. Why I am able to do? Because as my hand is moving, you see, as my hand is moving, the distance between this point and the tip of this is decreasing. Correct? As this pen is moving towards this point, the distance between this and my pen is decreasing. Okay? And my brain is taking note of this. So the stimulus for my brain to tell my hand to move forward is the proximity of this point with the tip of this pen. Correct? If the tip is very far off, my brain will tell my hand, come on, move. If the tip is, come on, move, come on, move, come on, move, come on, move, come on, move. Understand? So the input here becomes what? The distance between this point and the tip of this pen. Clear? So that becomes the input. And what is the output? With this input, how much my hand will move, that becomes the output. Okay, now my brain is watching this, because my brain is watching, because my hand can go here also, here also, here also. So my brain is getting the feedback. My brain is getting the feedback, and accordingly, it is telling my hand to adjust and go. So this is how our system works. I hope you got some idea about the feedback. Hello.
Yes,
So
sir.
this becomes this becomes feedback signal, and the distance between this point and the tip of this becomes the input, and how much your hand moves, the motion of your hand becomes the output, and the input is the proximity between the two. So this is feedback, this is motion, and this is the proximity. So this is how the system, our system is working. Our system is working. Okay, got it?
Yes.
Okay. Now, now this is the first thing. Now here you see the amplifier. The negative feedback is used to stabilize the gain. Okay. Now here, okay, I'll just remove this example. So it can so happen, that I wanted, see, for an input of, for a delta Vin of 1 millivolt, I expect the output to be 10 millivolt. I expect the output to be 10 millivolt. For an input of 1 millivolt, I expect the output to be 10 millivolt. Okay. So I would have designed the amplifier. I would have designed the amplifier to get this. That is RL, RI, and all I would have adjusted. But it can so happen that I want to take the right example because quickly I want to explain this to all of you. See, now the output can go plus, say, 2 millivolts or say minus 2 millivolts. So I would have designed it for this, but the output can go to this value or to this value. Hello, are you with me?
So like, is that kind of error, sir?
Yes, that's an error. Correct, that's an error. Excellent. Okay, now how this, see, I would have designed the amplifier transistor. How this can go to this value, because see, after all, voltage gain AB is equal to what? AB is equal to what? Beta times RL by RL. Correct?
Correct.
For a common emitter configuration. Correct? Now, listen carefully. This beta, yesterday you asked a question, Adil. What is beta? Beta depends upon how you have manufactured the transistor. You can manufacture the transistor for requisite beta. Correct? And the transistor working itself depends upon what? The concentration of the charge carriers. The transistor working itself depends upon the concentration of the dopants, the charge carriers, etc. Correct? And the concentration of these charge carriers depends upon what?
Doping, sir.
Correct. One is doping. Any other factor which will affect the concentration? Come on, basis of semiconductor. Basis of semiconductor. You have answered so many questions. Arey yaar. Tell.
Temperature.
Correct. Semiconductor devices, one of the important things is that, it is very sensitive to temperature. It is very sensitive to temperature. Okay. In fact, this beta is a function of temperature. Beta is function of many things. One of the things is it is a function of temperature. So you can very well see that if the temperature increases, beta can increase or decrease. I will not discuss that. Beta can increase or decrease. So beta will vary with the temperature, therefore AB will vary. If AB varies, then the output will also vary. Correct?
Correct, yes.
Understood all of you? So if the temperature varies, this will also vary. Okay? Now you have made a system using the transistor. Okay? And now if the temperature fluctuates, then your reading will also fluctuate. Your temperature fluctuates, the reading will also fluctuate. Then you cannot simply blame, hey, मैं क्या करूँ यार, temperature increase हुआ तो meter गलत दिखा रहे हैं. That is not my problem. You cannot tell like that. See, you have made a weighing machine using semiconductors. So you have taken 1 kilo peda. So 1 kilo peda, it will show 1 kilo peda. So you will take 1 kilo peda. But then you will use a physical balance and weight. So there it will show 900 grams. Then you will tell the दुकान वाला, अरे देखो ये physical balance में ये 900 दिखा रहे, आपका electronic balance दिखा रहे 1 kg. So आपने मुझे धोखा दे रहे, you are cheating. Then the दुकानदार will tell, मैं क्या करूँ, ये system ऐसा है. Then will you pay money and take the peda? Definitely not. You will say, तुम्हारा electronic balance तुम्हें मुबारक. तुम्हारा पेड़ा भी ले लो, मेरे पैसा वापस करो. है कि नहीं? ऐसा भी हो सकता है वो मीटर 1 किलो दिखा रहे, एक्चुअली इट इज 1100 grams, then the दुकानदार is at loss. Correct? हाँ. Hello, all of you are listening? ನೀವು ಒಬ್ಬನೇ ಹೆಸರಾಗತ್ತಿ, ಉಳಿದವ್ರು ಬಾಯಿ ಇಲ್ಲ, ತಲೆ ಇಲ್ಲ, ಕೈ ಇಲ್ಲ, ಕಾಲಿಲ್ಲ, ಸಂಬಂಧ ಇಲ್ಲ ಅವ್ರಿಗೆ, ಕೆಲವೊಬ್ರಿಗೆ ಹಂಗ ಕೂತಾವ್ ತನಕ. ಹಾ, so it can happen. So you cannot simply say, oh, what can I do? You cannot. Ha. So here you see, students, you will learn how to stabilize a transistor, how to stabilize an amplifier. That is, even though that, see now, if you don't stabilize it, then see now here the input here is say 1 kilo farad. Okay, and the output can be 1 plus or minus say 10% variation. That is 1 kilo. It can be 10% means it can be 1100 grams or it can be 900 grams. Correct? Correct? Now, I don't want this. I want my output to be 1 plus or minus 1%. Or even a better amplifier, it should be 1 plus or minus 0.1%. Correct? Understood? So this is what is called as stabilizing. Now, in an amplifier, negative feedback is used to stabilize the gain. So, if you stabilize the gain, negative feedback, then you can achieve these specifications. Correct?
Here negative feedback means change, sir.
Negative feedback means? See, I'll tell you. See, I have to teach you the design then, okay? Then only you will be convinced. So, should I teach you the design? It is not there for your syllabus. Shall I teach you? It will take your time. Or just be convinced. Just be convinced. Okay, sir. Yeah, so to stabilize. See, I have told you. What is the stabilization. See, now the temperature has increased or decreased, then you will get this variation. You will get this variation because of temperature. Now, I will do something. I will add a resistor to the transistor, or I will add some resistors to the transistor, and thereby I will be able to achieve this specification, or even better, this specification. And when I do add a resistor and get this, I am telling them the amplifier is stabilized. And for this, I will be using the negative feedback. Okay, if you are not convinced, I will explain. I don't mind, but your half an hour will go. If you are ready, I will explain. Shall I explain or shall I move on? Please, it is your life, your decision. Because if I complete the syllabus, I will have more time for revision. Choice is yours. You tell me fast. Shall I move on? Or shall I sit and do bhajan till all of you are thinking, Arun is not speaking today. I don't know what has happened to me. I think he is watching some movie, I think so. Or reading some Harry Potter. ಏನಾಯ್ತು ಅವರಣ್ಣ ಸುಮ್ ಕೂತಿಯಲ್ಲೋ, ಏನಾಯ್ತ? ಬೇಜಾರಾಗೈತಿ? ಯಾರೋ ಬೈದಾರ? ಮತ್ತೆ ಏನೋ ಆಗಿರ್ಬೇಕು ಕಾಲೇಜ್ನಾಗ. ಆಯ್ತು, ಈಗ ಏನ್ ಮಾಡ್ಲಿ ಹೇಳ್ರಿ? ಹುಡುಗರ ನೀವು ಏನ್ ಮಾಡೋದು ಗೊತ್ತಾಗೋದು. ನೀವು ನೋಡಿ ಒಂಥರ ಕಲೀಲಿಕ್ಕೆ ಬರ್ಬೇಕಪ್ಪ. You should come. Okay, I'll quickly explain. Now learn very quickly. Very quickly you learn. Okay. So what is the gain of the transistor here? AB will be equal to what? Beta times. Here.
Beta times
RL by RL.
Yes, sir.
RL by RL. Okay. So here, what is the input impedance that you see here? What is the input impedance that you see here? That is
RB plus R forward.
RB plus R forward, isn't it? So beta divided by RL divided by RB plus whatever is the impedance that you see here. It will not just be RF. It will not be just RF. Okay, it will not be just RF. Okay, I will write it as RF dash. Because see, in this for this junction, even this current will also be flowing in that junction. Okay, so therefore you have to take it as RF dash. Okay, hello?
Yes, sir.
Good. Okay, now let us expand this. This is what? This is IC into RL divided by you see here IB into RB plus RF. Correct? RF dash. Correct now? Hello. So IC is what? Beta times RB, it will get cancelled, you will get this value. Okay? Now let us understand the situation. If the temperature increases, beta will increase. If the temperature increases, beta will increase. Means what? For the same IB, IC will increase. Got it?
Okay. Yes, yes.
For the same IB, IC will increase. And therefore, the gain will also increase. Got it?
Yes.
Okay. Now, you see what I will do. Now, I will add one resistor RE. So, if I add the resistor RE here, okay, then how will this equation change? So, now here you see, here IC into RL. This will not change. Hello, are you with me? But as far as the input is concerned, on this RE, there are two currents that are flowing. What are the two currents? One is IB, other one is IC itself. See, this IC, this current IC here is flowing like this. IC is also flowing, but before RE was there, this IC was flowing. IC into 0 is 0, but now it is not this. So now here IC is also flowing, IB is also flowing. Can you see here? IB is also flowing, IC is also flowing. Do you appreciate that?
Yes, sir.
So now you see the situation here. You try to understand the situation. So this voltage now VE, what happened to this VE? This VE, if this IC increases, then what is the implication? IC increases, then VE will also increase. Correct? The drop here, man, VE is what? This current into RE. IC into RE. Hello? IC into RE will also increase. Yes or no? See, student.
The drop will increase.
See here. IB will be equal to water. VB minus VE divided by this resistance. Which resistance? RB plus RF. Correct now?
Yes, sir.
Okay, understood? Now if you add this RE, see, before adding RE, this was simply VB minus 0 divided by RB plus RB. And IC was simply equal to beta times IB. Got it?
Yes, sir.
So this is one situation. Now if I add RE, then what is the equation I have to write? I have to write here now VB minus, you see here, IB plus IC into RE divided by RB plus RE. Got it? VE is now what? IB into IC plus RE. These two currents are flowing here. So the voltage here will be what? Whatever current is flowing here into RE. Got it?
Yes, yes.
Yeah, useless fellows sir. Others sir?
Yes, yes, sir.
Others are not telling yes also, no also.
Yes, sir.
Okay. Adil, you understood?
Yes, sir. Understand.
IB plus this one. So what happened now here?
Yes,
You see?
sir.
Now you see here. So IB is equal to what? VB minus IB plus IC into RE. Okay? Divided by RB plus RE. Okay. I will elaborate this. So now here you see, if the temperature has increased, okay, I'll rewrite this. IB will now be equal to VB minus, see here, IB plus beta IB, because IC is what? IC is beta IB. Correct? Into RE divided by, I will take it as what? Divided by here. So here it is not just RB RF. Here it is not just RB RF, because this resistor also will come into picture. So this will be plus beta times RE. This will also come. So here I will get it as RB plus RF dash plus this RE is also coming here. Hello?
Yes, sir. RE becomes my beta type.
Because see, in this RE, not only IB is flowing, IC is also flowing now.
Correct, sir.
So therefore, if you take this, the effective value of RE seen at this point, it will be beta times RE.
Okay.
Okay, it will become beta times RE. Okay, I will not take this. Okay, I will just take this because I am only stopping at this point. I am only seeing this current. I will not take it. Okay, I will not take it. Leave it. I will only take it like this. Done. So now my equation now for IB will be what? VB minus IB into 1 plus beta into RE divided by RB plus RF. Correct now?
Yes, sir.
Now observe very carefully. If the temperature increases, what will happen? See, now you rewrite this equation. You rewrite this equation. What you have to see here is if the temperature increases, beta will increase. Hello?
Beta increase.
If beta increases, IB will decrease. Beta increased. So 1 plus beta increased. 1 plus beta increased, but there is a minus sign here.
Yes, sir.
So this quantity will increase. If this quantity increases, VB minus this quantity has increased means IB will decrease.
Yes, I will.
And if IB decreases, the IC will also decrease. Because IC is what? Beta times IB.
Correct.
You understand?
So that will maintain constant, sir. Beta and
so the जुगलबंदी चलता है. ये ऊपर गया तो ये नीचे आ जाएगा. Understand? So अभी देखो ये बीटा ज्यादा हुआ तो this voltage will increase, then automatically this current will decrease. If this current decreases, then this current will automatically decrease. If this decreases, again this beta will increase. So थोड़ा ये कम थोड़ा कम. So finally you see daga 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 okay, both will be stabilizing. Understood? So here you see if IC increases, this voltage will increase and decrease the input. IC output increased, input decreased. This is called negative feedback. See, देखो अभी तुम सब लोग very good students are there. Very good students are there. Okay. So one student, he would have got less marks in one test. So when they got less marks in one test means he will become mansik. Usually. Then he will say, I have become very mansik. Then he will say, I will go and drink. I will go and drink alcohol. You get those brads, no? I will go and drink. Then if you are a good friend, you will tell him, Ray, don't worry man, don't drink all that, it is very bad for health. So you don't get depressed and all, you will become okay, you study hard, then you can do well in exams. By drinking and becoming mansik, you will not get good marks. So you are giving what? Negative feedback, not to drink, and you are stabilizing the system. You are making sure your friend is stabilized. Understood?
Yes, sir.
Now your friend is say, I am going to drink, I become mansik. Yes, not 2 pegs, 4 peg piyo, to theek ho jayega. You are giving positive feedback. And you are going to increase his problems rather than decrease. Got it now? So positive feedback, negative feedback. So in order to stabilize, you are going to give negative feedback. This is one of the ways I have told you. There are many ways of giving negative feedback, etc. So by adding RE, you are stabilizing the amplifier against the temperature variation or beta variation. One example. Okay, done. See, listen students, I am a teacher. So if a student asks question, if the teacher knows the answer, he must give the answer to the student. That is teacher ka dharma. Okay, and how much ever the student wants to learn, the teacher must go on teaching the student till his knowledge is exhausted. Finally, when the student asks question, teacher doesn't know the answer, he will say, look, I don't know the answer for this, but the teacher should say, go to another teacher who will give you the answer. That is teacher ka dharma. अभी ये IIT मेंस वगैरह ये क्या हो गया, टीचर का धर्म गया. So you ask question, I know the answer, but I have to say in exam it will not be asked. There is no time. All that nonsense. Actually, in teaching profession, all this nonsense should not happen. But unfortunately, we have to do this. Anyways, so this time I have obliged you, but next time be cautious. Okay, so your time will be saved. As far as, because usually students give complaint to me, sir teaches theory very well, but he doesn't solve problems. I am ready to solve any number of problems, but time. But requisite science I have to teach you. That is my dharma. That I will not leave. I am not a teacher who will solve 1,000 problems and become very, very prominent. I want to ensure my students learn. They have got the knowledge. Anyways, it's up to you. Okay, shall I proceed?
Yes, sir.
Okay.
Yes.
Wait, there is something called impedance matching. There is something called impedance matching. Now, you have come across this term impedance matching anytime?
No.
Do you know maximum power transfer theorem? Hello, do you know maximum power transfer theorem which you have learned? No, don't say I have not learned. I have only taught you. Hello? Okay, there is a source B and it has got internal resistance R. Now there is a load RL. Okay, the load RL. Now I want to
Internal resistance should be equal to the resistance of the load. Internal resistance should be equal to the resistance of the load cell for maximum
this
power.
boy has got good memory. So if you see RL is equal to R, then this implies what? Maximum power transfer. Maximum power transfer. I think we have proved this.
Yes, sir.
So this is it. Now when you want maximum power transfer, but now when you want maximum voltage to go, to the output. Then you will make sure that RL is very, very greater than R. Then maximum voltage will be transferred to the output. Now if you want maximum current to be transferred, then RL must be very, very small compared to R. Then maximum current. Correct? Maximum current, maximum voltage, maximum power transfer. So this is the requirement. These are the requirements. Okay. So therefore now you see when you make one, see now for example, you make an amplifier. Okay. So you make an amplifier. Okay. So you are giving input, you are giving output. So this is input, this is output. So for Vin you will get output. So this amplifier will have gain AB. So there is something else also called as bandwidth. See, now please understand this. Now here you see, supposing I am singing. So what are all the frequencies I am emanating from my vocal cord? Usually, it's not one frequency, no. Hello, my sound consists of many frequencies. Got it? It has got many frequencies. Okay. Now, if you see very carefully, approximately the number of frequencies that are generated will have a bandwidth. Bandwidth means, see, I have got now frequency, so I'll be emanating this frequency, this frequency, this frequency, this frequency, this frequency, many frequencies. From F1 to F1. I'll be generating all these frequencies. Correct? Hello? So now a number Fn minus Fn. What is Fn minus Fn? A number. So supposing Fn is say 2 kilohertz and F1 is say 100 hertz. So 2 kilohertz minus 100 hertz will be what? 1900 hertz. So the bandwidth will be 1900 hertz. Got it? So if at all I am speaking, I will have my characteristic frequency here. But around these characteristic frequencies, I will be generating so many frequencies. That is the quality of my voice. Supposing somebody else, say Abhirav is singing, or Adil is singing, or Aniket is singing, then his characteristic frequency can be different. Obviously, it is different. That is why if Aniket says hello and if I say hello, you can distinguish who is telling hello. Characteristic frequency. But along with the characteristic frequency, there is a band of frequencies that we emanate. Okay, so that is called as bandwidth. Got it? Now, these amplifiers that I am discussing are real. Real means what? They don't have unlimited capacity. All the realistic things in this world do not have unlimited capacity. Got it? There is a limitation. There is nothing like unlimited. Okay. Hello, I hope you are getting me. See, infinity is only an idealized term. Okay. But in reality, no. Okay. See, you take any vehicle, any car, any bus, its speed is limited. You cannot have unlimited speed. Clear? Hello?
That's yes.
So, one is that the amplifier will have gain, voltage gain. So, there is limited. You cannot have 10,000, 20,000 voltage gain, just like that. So, one transistor, one amplifier can have maximum of so much, so and so gain. It cannot have more than that. Okay? Got it?
Yes, sir.
But supposing, see, now with a particular configuration, with a particular brand of transistor that I have taken, and it has got certain beta value, so I can make an amplifier of gain, good amplifier of amplifier gain 10. Amplifier gain 10. But supposing the requirement is I want to have an amplifier of gain 100. Now please understand this. So I can make an amplifier AV whose gain can be from, I can make an amplifier whose gain can be 1 to 100. I can design an amplifier for this. Obviously, what I have to do, when I take a transistor, its beta value is fixed. All that I have got to choose is the value of RF. So I can set it to a gain of 1 to 100. Got it?
Okay, yes.
Simple. But there is also something. See, now supposing I am doing audio amplification. Audio means, say I am singing. Then it has to amplify the signals of different frequencies. Got it? It has to amplify signals of different frequencies. Now, every amplifier will have bandwidth. Okay, you will understand this. So, for every amplifier, this quantity, AV into bandwidth. Okay, this is constant. AV into bandwidth is constant. Got it? That means, now you see, I have made an amplifier configuration. Say, now if you are taking a band gain of 10, then you can have a bandwidth of 1000 Hertz. So 10 into 1000 will be 10,000. This is a constant quantity. Now what it means is, if I make the gain 100, then I have to sacrifice the bandwidth. Correct?
Okay.
So the gain bandwidth product of an amplifier is constant. Got it?
Okay.
So therefore, now you see, for example, now I want a bandwidth of 1000. I want a bandwidth of 1000. Then I have to settle for a gain of only 10. I have to settle for a gain of only 10. Got it? But now the requirement is for a gain of 10, now only 2 audience can hear. So if I want 100 audience to hear, the gain must be 100. So what will you do? So in that case, what will I do? I will now configure the amplifier like this. So this is amplifier 1, amplifier 2. So this has got a gain of 10, bandwidth of 1000. This has also got gain of 10, bandwidth of 1000. Correct?
Yes, sir.
Now the combined amplification of these two. So this signal will get amplified, and again this signal will get amplified. So what will be the total amplification? A is equal to A1 into A2. So 10 into 10 becomes 100. Required gain. Did you understand? Hello?
Yes, sir. Correct.
So if I can connect to in series, I will get. But the bandwidth will still be 1000. The bandwidth will still be 1000. Is that clear?
Correct.
So see, I have to now connect the 2 amplifiers in series. Got it? I have to connect the 2 amplifiers in series. Now try to understand this. So here I am going to give the input signal, and here I am going to get the output signal, and again here. Now the output impedance of this, or the output resistance of this, and the input resistance of this. So now here you see the output. If the output resistance of this is equal to the input resistance of this, then I will have maximum power transfer from here to here. Got it?
Okay.
So understand? So you will learn about all this. So therefore, you need to ensure that the impedance matching also takes place between the two. And if the impedance matching doesn't take place, then most of the signal will be wasted here, and therefore you will not get the gain of 100. So therefore, in between you will be adding one more configuration which will ensure that impedance matching takes place properly. That is why you will go for some from amplifiers whose main purpose is not amplification but impedance matching.
We'll put one more amplifier there.
We'll put one more amplifier. See, amplifier means, you please understand. See, amplifier doesn't mean it will only increase the loudness. Hello? Amplifier means it will change one of the parameters or one or more of the parameters. It can either change input resistance or output resistance or current gain or voltage gain or power or many of them.
Okay, sir.
अगर इनपुट रेजिस्टेंस चेंज हुआ तो भी उसको एम्पलीफायर ही बोलेंगे.
Okay, sir.
ठीक है ना, मालूम हुआ ना. It will change one of the parameters.
Okay.
Got it? It will change one of the parameters. That is called amplifier. See, these are all the things you will learn in the classroom if you are good students. So therefore, I will be using some amplifiers, okay, only for impedance matching. That is what is it. CC is used for impedance matching connecting two transistors in cascade. Now, did you get an idea? Common collector configuration is also an amplifier, but its main job is to do what? Impedance matching.
Okay, yes.
Okay, see.
Yes, sir.
See here, common collector. What is it? So for impedance matching. So you can see the input resistance is very high, output resistance is very good. Okay, so that is best suited for impedance matching. That configuration. You will learn. देखो अभी PUC 2 में अरे यार देखो एम्पलीफायर डिजाइनिंग में ऐसा नहीं कि एक सर्किट दिया वो डाल दो हो जाएगा, ऐसा नहीं. Depending upon the situation, with whatever resources are available, you will have to give an optimum design. That is engineering. Okay, तो उसको दिमाग खर्च करना पड़ता है, वो फार्मूला डाल के नहीं कर सकते, दिमाग खर्च करना पड़ता है. ठीक है. So if you understand these things, you can do it. Okay. Okay. Now we shall solve some numericals, so you'll be happy. First, a transistor is a current operated device. Why? Can you tell the answer? I have explained now.
Current operated device means?
Current operated device means the output of a transistor is what? Is a current source controlled by an input voltage source.
Yes.
That's precisely what I have explained, isn't it? It is I have given you the model there, isn't it? So a transistor is current operated. That means you are creating a current. Transistor means the transistor. What I have explained the working of a transistor. I explained the working of a transistor. So what do you get? You get a current source, okay, which is controlled by a voltage source. So current source controlled by voltage. That is why it is called a current operated device. I have already explained all this to you.
Yes, sir.
The action of a transistor is controlled by charge carriers electron. That is why a transistor is a current operated device. No, you can write a better answer than this. Right? The charges, see, when the emitter base junction is forward biased and the collector junction base is reverse biased, and in a transistor, the majority of the charges, the majority carriers in the emitter region, when they enter the base region, and most of these majority charges in the base region becomes minority charges, and because of the reverse biasing of the current base junction, they will move into the collector zone, or bypassing or overcoming the high resistance that exists between the collector base junction. And therefore for small load resistance, okay, the current passing through the current base junction acts like a constant current source, and this current is controlled by the IE, and IE is controlled by the VIN. VIN controls IE controls IC. Got it? And that is why it is current controlled, a current controlled by a voltage source. Voltage controlled current source.
Yes, sir.
Okay.
Yes, sir.
I have explained this, you can write it nicely like it. So in a transistor, reverse bias is quite high as compared to forward bias. Why? Then only the transistor action will take place. Isn't it? Because transistor action is what?
Yes.
You are making the current, you are making some current to flow through a low resistance region. And it is very easy to make a current change in the low resistance region. But the same current is made to flow through high resistance. Okay, the same current. See, you are creating a current from the emitter base junction, for which you have to put very little effort. That is, you have to change the voltage very small. But the same majority of this current, 95% of this current will travel through the high resistance region between the collector base junction into the load. So therefore, it acts like a current source. And that is why the transfer of the current from low resistance to high resistance, that is why it's called transistor, transfer of resistance. Attractive force and all, I told you, no, it will pull the charges. Okay? Okay?
Yes, sir.
Transistor is a temperature sensitive device. Explain. Transistor is made up of semiconductor, P-type and N-type of semiconductor materials, and semiconductors are very much sensitive to temperature. You can write that equation. In other words, the concentration is proportional to T raised to 3 by 2. T raised to 3 by 2. It is it is proportional to this. Therefore, it is sensitive to temperature. Excess heat, complete breakdown and all, don't write on this. Don't write on this. This is not necessary to read. Okay, you can just say it is temperature sensitive. Okay, and if you want to elaborate, you can say the beta, alpha, beta, gamma of the transistor depends upon the temperature, because they depend upon the concentration of the charge carriers. As temperature increases, due to the breaking of covalent bonds, the concentration of the charge carriers increase, and thereby the beta of the transistor will vary. Okay, that is why a transistor is temperature sensitive. Or many other parameters of a transistor will vary. Correct?
Yes, sir.
The use of a transistor common emitter is preferred over the common base configuration. By common emitter, you will have both voltage gain and power gain is better than the common base region. Therefore, it is most preferred when it comes to voltage gain and power gain. Okay? When it comes to impedance matching, common base only is better. Okay? Okay. Why do you prefer transistor over vacuum tubes? Before transistors, there was something called as vacuum tubes. Right? So in vacuum tubes means they used to have a tube, there used to be vacuum, there used to be a cathode, there used to be an anode, and then they used to heat the cathode, and the anode used to be made the opposite potential, that is the electrons accumulated on the surface were pulled by that, and therefore again you are able to control the passage of the charge carriers in vacuum by controlling the voltage. So what you are doing in a semiconductor is basically you are using the voltage source to control the current. So there also you are using the voltage source to control the current in a vacuum space. Okay, those are vacuum tubes, but they are very bulky, it leads large voltages and lot of heat is wasted. So many things are there, and therefore we prefer transistor semiconductor version for this, and semiconductors are cheap and they are very, very light in weight. Vacuum tubes are very, very large. Anyway, I don't think it is there for your syllabus. When we studied, we had to study the vacuum tubes and this. But anyway, if a question is asked, you can just understand this. Correct?
Yes, sir.
Why transistor cannot be used as a rectifier? This you should answer. This my student should answer. Understand rectifier, draw a PN diode, and draw a transistor and say why you can't use this as a rectifier.
Sir, sir, rectifier used to convert the maximum AC current to DC form, sir.
Yeah, maximum AC current. क्या बोल रहे हो तुम?
Like what AC current we supply, sir, convert that into a kind of DC form, sir.
Sir,
So, but in a transistor, what happens is the AC component is amplified.
See, I just told you what an amplifier is. Okay, amplifier means changing one of the parameters.
Yes, sir.
Now, here you pinpoint on the question. They are telling you why you can't use it as a rectifier. See, you should be a student of science. You should be a student of science. Okay. See, in a rectifier, you are using a. Tell. Try.
In a rectifier, we will be using a diode, sir. And in that case, both of them will be similarly doped. But here, the transistor which is there, sir, the doping will be different, sir. Like one will be heavily doped, one will be very lightly doped, sir. As in the case of base and all that. That is why we cannot use it.
Yeah, correct. Your answer is correct. Your answer is perfectly correct. Correct. But you have to tell why. You are told the reason is this. You are right reason, but you have to explain. Hello, B.
Yes, sir. Yes.
You have to explain. See, the answer is correct. See, in a diode here, see, when you use this diode, so the doping concentration is same on both sides. The doping concentration is both on same side. Got it? That is, the doping concentration here is same. Therefore, this will work like a rectifier because it not only should allow the current to flow easily in forward bias condition, but it should have capacity to block the current in the negative direction. Got it?
Yes, sir.
Hello, Adil. Others?
Yes,
So that is possible if the dopings are same on both sides. Here you see the doping is different. So here you see the current, if this is it is forward bias, easily the current will flow in this direction. Okay? But when you reverse bias this junction, then because this doping of this is lower than this, the blocking capacity is very less. And therefore, this will not work like a perfect rectifier. It can work like a rectifier, but it will not be a good rectifier. Okay, because its capacity to block is limited. Right? And because of the differential doping concentration, you can't use the transistor for a rectifier. Okay? That's the thing. Okay, hello, can I continue?
Yes, sir, yes.
In a transistor, the value of beta is fixed. Calculate the value of alpha. I think you should be able to do this. Right? Simple. What's it? Beta is equal to alpha divided by 1 minus alpha. You can derive this formula if you don't remember this formula. So, how will you derive? IE is equal to IB plus IC. Now, if you divide this by IC, then you will get IE by IC is equal to IB by IC plus 1. IE by IC is what? 1 by alpha. And IB by IC is what? 1 by beta plus 1. Okay, so you simplify this. So you want in terms of beta. So you push the 1 here. So you will get here 1 minus alpha divided by alpha is equal to 1 by beta, or beta is equal to alpha divided by 1 minus alpha. So substitute the value. With the value of beta, calculate. So beta value is given as 15, and then you should calculate the value of alpha. Got it? Hello?
Yes.
That's all. But don't try to by heart the formula. In examination, you should do this. Yes, 0.9. Calculate the collector and emitter current for IV is equal to 20 microamperes and beta is 100. Okay, I think you can do this. Okay, so they are giving you the value of IV as 20 microamperes and beta value is 100. Okay, then calculate the collector and emitter current. Okay, so what will be the collector current? So it is beta times IV. Correct? So it will be 100 into 20. That is what? 100 to 20 microamperes. So it will be 2000 microamperes or it will be 2 milliamperes. And emitter current. Okay. So emitter current will be what? Emitter current will be, if you know collector current, you can find emitter current. So the emitter current will be what? It will be IC by alpha. Emitter current will be IC by alpha. Correct now?
The IC plus IV you can
IC plus
IV.
Correct. Finish. You are a much brilliant student than me. IC plus IV. Correct. Correct. So that will be 2020 microamperes.
Yes.
Correct. Very good.
Yes.
Yes, you have done IC plus IV. Correct. For a common emitter amplifier, gain 50 if the emitter current is 6%. Calculate the collector and base current. Also calculate current again. The emitter is working in common base configuration. Okay, do you want to try it out?
Right.
Do.
Yes, sir.
None. Good.
Yes.
Good.
Yes.
So I think you did this. And IB will be minus. Yes. I think you all did this only now, like this. This. You all did like this only? Hello?
Yes.
Also calculate the current gain when working as common base configuration. Common base configuration, Common base configuration. Yes.
And alpha.
So this is IE and this is IC, alpha. Right. So we will calculate alpha for this. Alpha. Very good. Alpha. So yes, 51 IB. IB is equal to so and so. Hence, IC will be equal to 50 into 51 divided by 6.6. Alpha will be so and so. Correct. And the gain will be alpha. Correct. Okay. Shall we continue tomorrow?